In this video, I'll be discussing how to solve equilibrium concentrations using quadratics. So up until now, you've been able to solve for concentrations of products and reactants at equilibrium without using quadratics. Now we're going to introduce the quadratic component for how to solve for those concentrations at equilibrium. So we've got this reaction here. We've got phosgene gas at equilibrium with carbon monoxide gas and chlorine gas. And the question says, if 0.4 moles of phosgene gas is placed in a sealed 5-liter vessel, what will the concentrations of phosgene gas, carbon monoxide, and chlorine gas be once the reaction is allowed to reach equilibrium? So the first thing I would do is I would go ahead and set up your ice table for this reaction. So here's the blank ice table for this reaction. And before you start filling it in, it would be a good idea to go ahead and solve for the concentration of phosgene gas. Because in the question they tell us that we have 0.4 moles in a 5-liter vessel. We can use those two values to solve for the molar concentration. You simply take the moles of gas, so 0.4, divided by the volume, which is 5 liters. And you always want your volume to be, of course, in liters. So doing that, you should get your concentration as 0.08 molar. And that's going to be the initial concentration of your phosgene gas. And at the start of the reaction, we haven't made any products yet. So our initial concentration for carbon monoxide and chlorine is going to be 0 for each. Now over the course of the reaction, these are going to change over the course of the reaction by a factor of x. Each of these has a 1 in front of them, so they're going to change by a factor of 1x. So for phosgene, it's going to decrease by a factor of 1x. For carbon monoxide and chlorine, they're both going to increase by a factor of x over the course of the reaction. So once these reach equilibrium, the concentration for phosgene is going to be your initial concentration minus that x factor that you change by. For carbon monoxide and chlorine, they both started at 0 and they both changed by a factor of 1x. So at equilibrium, their concentrations are both going to be that x value. So now that we've filled in the ice table, we can go ahead and write out our equilibrium expression for this reaction. So here would be your generic equilibrium expression for this reaction. So we've got Kc is equal to the concentration of carbon monoxide times the concentration of chlorine divided by the concentration of phosgene. If we plug in our values into that expression, we'll have our Kc as 8.3 times 10 to the negative 4 equal to x times x divided by 0.8 minus x. And again, these values are coming from the equilibrium part of our ice table. So now we need to take this equilibrium expression and convert it into the form of a quadratic equation. And if you don't remember what the standard form of a quadratic equation is, it's ax squared plus bx plus c equals 0. So we need to take this equilibrium expression and convert it into this form. So let's go ahead and step through the algebra of how to get this into quadratic form. So the first thing you want to do is take your numerator and multiply those two x's together to get x squared. Then you'll take your denominator, multiply it to the other side, and then you'll distribute that 8.3 times 10 to the negative 4th to both of those terms. and that will give you 6.64 times 10 to the negative fifth minus 8.3 times 10 to the negative 4x equals x squared. Now we need this to be set equal to 0, so we're going to rearrange this equation in order to get everything on the same side, and that way it can equal 0. So once you do that, you should get x squared plus 8.3 times 10 to the negative 4x minus 6.64 times 10 to the negative fifth equal 0. And that is in our standard form of quadratic equation. So now there's a couple different ways you can solve for x. And that's going to depend on if you want to do it by hand or if you want to do it using technology. So if you want to do it by hand, of course, we'll have to use the quadratic formula, which if you took algebra in high school, you most likely had to memorize at some point. Or if you have a graphing calculator like a TI-83 or a TI-84, you can actually program the quadratic formula into your calculator. And when you do that, it just takes 5 seconds to punch in the values for the formula and solve for it and get your value back for x. Up to you whether you want to program the quadratic formula into your calculator or not, but let's go ahead and do it by hand, that way you'll know how to do it in case you don't want to program it into the calculator. So we're going to be using the quadratic formula, and that is minus b plus or minus. However, in this case we only care about the plus value. So plus the square root of b squared minus 4ac, and this is all going to be divided by 2a. So now to solve for this, you just take your values for a, b, and c from your equation and plug them into the formula. A is going to be the term in front of the x squared, which in this case is just 1. B is going to be the term in front of the x term, which is 8.3 times 10 to the negative 4. And c is going to be that constant at the end. So in this case it's negative 6.64 times 10 to the negative fifth. So now you can plug all these values into the quadratic formula. So here's what your quadratic formula would be if you plugged in all your values for a, b, and c. And if you do all the algebra here and plug all this in, you should get your x value equal to 0.008. So now that we've solved for x, we can revisit the ICE table and solve for our values at equilibrium, plugging in for x. So for phosgene gas, the concentration at equilibrium is going to be 0.08 minus x, which is our 0.008. And that will give you an equilibrium concentration of 0.072 molar. For carbon monoxide, our value at equilibrium was just x. So its equilibrium concentration will be 0.008 molar. Same thing for chlorine. Its concentration at equilibrium was x. So we just plug in for x and you'll get 0.008 molar for chlorine gas as well. And that's how you use quadratics to solve for the concentrations at equilibrium.